All right, so let's start with a review of our valence electron pattern as we go across the top of our periodic table. So we learned last chapter that in group 1, all of our elements there have one valence electron. Remember, that's an electron in the outermost energy level. In group 2, they have 2 in the outermost energy level. We skip the transition metals because they don't really follow the same pattern. We come all the way over to group 13, the boron family. They have 3 valence electrons, and then so on and so forth, all the way up to 8 in our last group, group 18, our noble gases. And we said that most of them have 8. That's why I put a little star there. The only one that doesn't is helium. It only has 2. But we put it in the noble gases since it's also stable, or its outermost energy level is full, because it's only trying to fill the first energy level, which can hold 2, and it happens to have 2. So this unit, we're going to expand upon that a little bit more and talk about how these elements can share electrons, like we talked about with covalent bonding, but they can also give electrons away or take electrons, and that's going to cause an ionic bond. So anytime one of these changes how many electrons they have, and therefore the protons and the electrons don't match anymore, it's not going to be a neutral atom anymore. It's going to be what we call an ion, because it's going to have a charge. So in our first group, since they have one valence electron, we've learned that they tend to give that one electron away to one of our other elements, possibly something on this side of our periodic table. And so when they give away an electron, there's one less negative charge, because we know electrons are negatively charged. So that means there's one more proton than electrons, so it ends up with a charge of +1. And just like we saw with our valence electrons, again, all of them have 1, so these would all have a charge of +1 when they are an ion. In group 2, they will be able to give away those 2. So again, a reminder, our goal here in most cases is to have 8 valence electrons, because usually 8 is what it takes to make it stable or the outermost energy level be full. So if they have 2, they can either give those 2 away, or they can take 6 from other elements. And it's easier energetically to give those 2 away. So these ones have a charge of +2. We come over to group 13. These ones have 3, so they can either give away 3 or take 5 to make their 8, and it's easier to get rid of 3. Now, this next group in general, they don't, so especially the ones at the top here, they tend to do more sharing of electrons instead of giving and taking them. But for the sake of our pattern, since they have 4, we like to think of this group as the plus or minus 4 group, because they could give 4 away to be stable, or they could technically take 4 in order to be stable. Group 15, so 5 valence electrons, they can either give away their 5 or they can take 3. And so it's going to be easier for them to take 3. So now if we're taking electrons, we have more negative charges. So instead of it being a positive charge now, it's going to be -3. So if you have 3 extra electrons, you'll have a -3 charge. If we have 6 valence electrons, we can either get rid of those 6 or take 2. It's easier to take 2, so they have a -2 charge. Group 17 are halogens. We know they have 7. We know they want to have 8. We know that it's going to be really easy for them to just take 1 electron from someone else. Again, if I have one more negative charge, I have a -1 charge for each of those elements. Now our noble gases, we know they're already stable, so we know they don't need to share electrons. They don't need to give or take electrons either. So they will end up with a charge of 0. They won't change the number of electrons, so their protons and electrons are still the same, because they didn't need to do any giving or taking. Thanks for listening.